Hello. Yes, we're working. Great. It's the first conference I've ever been to where everything just kind of magically worked the second I stepped on stage. So thank you very much to the audio and visual crew here for making that an incredibly easy process. My name is Stephen Vittitoe. I work for Google on the Project Zero team. Relevant contact information is here. If you have questions or you want to get a hold of me or complain to me, you'll find my Twitter handle and email address. I also play a lot of Capture the Flag, so I play on the Samurai CTF team. And if you want to play CTF, I would encourage you to do so. It's a great way to take reverse engineering skills and apply it directly to vulnerability analysis, which is really kind of how this research started. I was hunting for bugs in AFD.sys. And while I didn't come away with any bugs, I came away with a pretty good understanding of the driver and felt that worth documenting. So an outline, we're going to talk about why I was even looking at AFD.sys to begin with. And it's not because it starts with A. I didn't just list all the models and say, well, we'll go with that one. We'll give you a kind of WinSock overview. AFD is a part of this overall system architecture in Windows called WinSock. We'll tell you some of the interesting findings I had in the driver itself, tell you how you can talk to it, where it initializes from, and how you can use it to your own benefit. And I'll tell you about the vulnerability analysis I performed on it and some of the fuzzing work that I did. And then we'll kind of wrap up with what I'd like to do with this in the future, and hopefully we can encourage other people to get involved with this kind of research as well. So what is AFD.sys? It's a default kernel module is in System32 drivers. You can go and look at it and get the file properties on it, and you'll see it says the ancillary function driver, which there's a story behind this name, actually, that it used to go by a different name. Does anyone know what it is? Yes, sir. Another fucking driver. So you can imagine the guy just sitting down programming drivers all day long, and at the end, he has his 30th driver to program. He's like, another fucking driver, and he names it that in the initial stick, but he has to change the name before release. So ancillary function driver, which is the ring zero entry point for socket. So when you do a socket call, you bounce around in this user mode architecture. It doesn't actually do anything for you until you hit kernel, and we'll tell you more about how that works. So not everything in Windows uses AFD for network communications, and Microsoft is sort of notorious for this, of building the same systems to do different things. So you could talk to the network by at least 4 different ways. So you've got AFD, you've got WinHTTP, which will go through HTTP.sys, you've got WinINet, you've got WebDAV for communications, and you've got MRX SMB for SMB clients. So basically, networking file systems and special optimizations for internet-heavy communications. But this is the one that was really interesting to me, with the BSD socket APIs. And why we're interested in it, not because it starts with A, but because it is very accessible from sandboxes. So if you look at the Chrome sandbox, the renderer process, for example, has accessibility to read devices' AFD endpoint. You can open it, you can send ioctls to it as even a guest user on your system. Same with Adobe Reader, and same with IE-EPM. In fact, every sandbox that Project Zero looked at, and really James Forshaw on Project Zero looked at, had this device accessible. So despite the fact that you can't initialize WinSock in the Chrome sandbox, you can't call WSA startup, you can open the device AFD and send ioctls to it to make your network communications without the benefit of the user mode WinSock framework. So this is immediately interesting, because you get this functionality by sort of bringing your own WinSock along in shellcode or whatever you have. And for bugs, there's a history of bugs. There's been about one good one a year. One of these was an information leak, but the one last year in 2014 was a full-on privilege escalation that was really, really well documented, and actually ended up being used as part of a chain of bugs to take a $100,000 prize away from opponent-owned competition. So Google was naturally interested in this as well, and continued to do some of this research. Okay, so as I said, I work for Project Zero, and sort of the one-line mission statement of this team is to make 0 days hard, or not impossible, but more difficult, so you can't spend a week fuzzing something and walk away with a 0 day that'll get you on 100,000 computers, right? So we need to make that a more difficult process, and we have 3 approaches to do that. The first one is to make sandboxes more difficult. So sandboxes are, a widely adopted technology already. You see them, like with Chrome, IE, Reader, and Office apparently now too, right? So the idea behind them is to increase attacker cost, so you have to use an exploit to get into the sandbox, and then an exploit to get out of the sandbox. So we feel that the process of getting in is easy, and that's the second approach, is we'll make that harder by fuzzing out low-hanging fruit, and we'll do a lot of manual analysis on the sandbox to make getting out harder as well. So we've historically sort of seen three big ways of getting out of sandboxes. The first one is logic errors in a broker process, where you have a sandbox and you can't write any files, you can't make any network communications, you can't do any registry reads, except you actually do need to pull this configuration. So you talk via IPC to another process that has the permissions to do what you need, and then you can get in just that one narrow path. And sometimes there's a lot of these things that are exceptions to a sandbox, and we'll find logic errors with those things. A sandbox is only as strong as the kernel that it's running on, or the accessible part of the kernel that it's running on. And you find things like Win32k sys coming in at 3.1 megabytes with an extra, I don't know how many hundreds of system calls that you can hit off of that. And these are both well-known things. The one that you don't see a whole lot of people talking about was accessible devices. So AFD being accessible, there's also like your USB hub is accessible through most sandboxes as well. So this is sort of a not often talked about attack surface for the Windows kernel and sandbox escapes in particular. And you actually can't even disable this thing until Windows 8. So you could go in it with an administrator and change the permissions on the device, but then no one can make socket calls on your computer, which is not something you want to do. In Windows 8, you can use like an app container with a lowbox token and disable that specific file, but that's not a simple process to do. It's not like, say, restrict it for one particular usage or technology. It is something that is always there and has always been there. In fact, it actually dates back to Windows 95. So if you fire up a 95 box, you'll see AFD.sys running and doing much of the same thing that it's doing today. So we have this kind of like perfect storm of complexity and accessibility. And when I say complexity, like you can take a real quick blush at it and you see that it's 500K. Most drivers, if you look at just kind of average sizes, are less than 100K. It's not as atrocious as a 3.1 megabyte driver, but it's still quite sizable. And it will handle 70 ioctals, well, 71 ioctals out of the box directly off of the endpoint. And it is designed to map between different protocols. So it's handling everything from TCP/IP, IPv4, IPv6, TCP, UDP, raw sockets to SAN requests. So there's quite a lot going on here that it's trying to account for all at once. This is a very dated diagram, but it kind of gives you an impression of where WinSock lives and how it works, and where AFD fits in that picture. So across the top here, you'd have your applications. These will largely be Windows 32, 64-bit applications. They'll talk to WS232 DLL directly now, so you don't see this old like WinSock import directly from WinSock 1.1 back in like Windows 98, 2000 days. The application will call socket. So if you started off your application, you did socket, AFINET call. You'd have to initialize this first, obviously, so it's WSA startup, which will load all these DLLs into memory. But the socket function first goes to WS232, where it immediately calls the WSA version of socket. So you see this a lot in Microsoft code, where you have a wrapper with one function call just calling off to another one with the exact same arguments, maybe a couple of them are null. And then from here, that pretty much gets out of there really quick too and goes off to mswsock.dll, which is where a lot of the functionality is actually implemented. MSWSock then has an abstraction to say which protocol do you actually want to talk to. So in this case, we're saying we want to talk TCP/IP or AFINET. We could pass in AF/IRDA, and we would be speaking infrared as well. And there's a different helper DLL for each protocol that you could load. And this is all very well documented and understood in Windows and how to write these helper DLLs. So I won't spend a whole lot of time going on with it, but basically we bounce to the helper DLL and then back out to MSWSock, and that's where ioctals start to happen to AFD.sys down here in kernel mode. So it's the first stop in kernel mode. When you make a socket call, there's actually 3 ioctals that happen. The first 2 pull information about the specific protocol, the specific socket type you tried to open, and then they set the information into an AFD structure that is created when you first open AFD endpoint. So that will contain your unique data about this is for AFINET, this is a sock stream socket, and that will control how AFD reacts to the rest of the endpoint as off of this initial setup. This is kind of funny too. So Microsoft is very, very good about being backwards compatible. And if you go and you look at some of these files on here, msafd.dll is literally an empty PE file. So it has one export shim to point to MSWSock, but otherwise it is pretty well defunct, and but still exists as an artifact to provide compatibility. So in this way, AFD really acts as a translator between multiple protocols that can be specified in user mode and a lower level kernel abstraction. So AFD is not your network driver. It's not sending out your packets, but it is translating your calls to either TDI or WSK. And WSK is WinSock kernel, so they've sort of extended this user mode architecture down throughout kernel mode. And TDI, Microsoft has said they're going to deprecate it. You shouldn't use it anymore. And like things like layered service providers, you now have to use a Windows filtering platform. It's still there, and when you're making a plain socket call, this is what it's going through. It's still going through TDI. So kernel mode clients that want to open a socket can use WSK to open a socket, and this is actually implemented also in AFD.sys. So AFD.sys becomes a WinSock kernel provider, and you can see it registering for all of these inputs as well. Unfortunately, you cannot hit the WSK code from user mode, otherwise really interesting things would happen, and that would be a topic for vulnerability analysis all on its own. My interest was simply what was accessible from the sandbox, so I was looking at the root 70 or 71 ioctls that you can hit. So you open up the driver, and the first glance you notice there's tons of debug prints. There are like 113 cross-references to it, and there's like 1,000 functions in there, so 10% of the functions had debug prints in them. And normally you think about, well, I should remove debug prints on release builds, or use the ETW, event tracing for Windows, which also accounts for a significant amount of code in this driver. And you see the debug prints going up over time, so 23 to 113 between Windows 7 and Windows 8. I'm not really complaining about this. It makes reverse engineering this actually a lot easier, because it will tell you, at this offset, this registry needs to be printed out, and the value of whatever structure offset it was will be printed to you in plain text. So this was both useful for reverse engineering and for turning on the debug prints to come back to a kernel debugger so that you could watch what was happening. And the check build does similar things. So the first thing it does, it creates this device, and then it starts reading in configuration from the registry. My best guess as to why this happens is so that you can have an AFD that is tuned for a client machine that is the same code but tuned differently for a server machine, for a phone. So it will receive all of these different configuration settings. Normally things like buffer sizes were in there. That was interesting. If you have raw security enabled, so if you've ever tried to open a raw socket after XP Service Pack 2, you're going to get access denied unless you have a registry bit flipped here, and there's one for AFD, and there's also another one for TCP/IP. So this is a common configuration setting for drivers. And then you actually see protocol-specific things coming from this configuration as well. So default send windows, the TCP windowing, that you can actually adjust that in your registry. And it's very easy to find all of these configurations. You just run strings on the binary, and you'll see all of them. And this fills out this AFD config info structure that's referenced all over the place. The buffer sizes one, for me as a vulnerability analyst, caught my eye, because if you start a driver and then it has a certain buffer size configuration, and you can change that as it's running, well, one buffer size is not going to be the same buffer size between other runs or other calls to it. Unfortunately, well, fortunately for the security, the keys are appropriately secured. You have to be admin, and if you're already admin from a sandbox, there's a lot easier ways you can do to escape a sandbox. Now, a few of these configurations are registered as volatile configurations, so that they register a change event notification on the registry. So the driver will get a callback when this registry key changes, and it will reconfigure itself. Things like buffer sizes are not in that, and the disable raw security was not in that, which is why you have to reboot after setting this flag if you want to make a raw socket communications. So let's talk about inputs. This is really what matters when we're talking about what does it do with the data I want to give it. Drivers usually receive inputs off of ioctls, and this is indeed where the majority of the cases here. You can see that everything is set to AFD dispatch. Then they have a few different dispatch controllers. So AFD dispatch device control is the one that I focused on. There's a WSK dispatch for internal only, event tracing dispatch, and then there's a fast IO path, which mostly maps back to other dispatch device controls. And of course, an unload, which is mandatory for drivers. It also registers plug-and-play events. So when you plug in a new network card or a new infrared device, AFD is going to get a notification about that as well. And then likewise, it is aware of the TDI layer, because that's who it is a client to TDI as it is a server for user mode. It is aware of TDI address changes. So if we have a new device plugged in and it gets an address, AFD maintains a list of those addresses for use in other user mode socket calls. And then as things developed and Microsoft put RPC in the kernel, AFD was not immune from this as well. It has several imports from MSRPC. I haven't reversed those yet, but RPC in the kernel really sounds like an interesting thing, doesn't it? So this is the big ioctl table. Again, it's easy to find. It's set at the bottom of GS driver entry. And immediately after it are the numbers of the ioctls. So basically, the first thing on the list for the ioctl table matches to the first function. And those are the symbols if you wanted to go and pull them. There's actually another level of indirection happening here, though. So if you look at this, you can probably see that, like, I don't know, yeah, that works. So, like, these are all AFD dispatch immediate. And they have different numbers associated with them, but it's always going to the same function. So basically what's happening there are those are the ioctls that will always return an IOF complete request immediately. So they don't say status pending. And this is where the fast path things map to as well. And so just an example, so there's another table here. So off of call dispatch, there's the another table that's referenced inside dispatch immediate, and these map one-to-one with nulls for the other ioctls that come in. Kind of interesting here as well is that you find that there's overlap between the functions off of the fast path as well. So like several of the ioctls for dispatch immediate all point to get context or set context. And these are for setting different kinds of information on the socket, and it defines that by ioctl number. Right, so static bug hunting. I mostly focused on Windows 7 x86. I wish I would have started with Windows 8. The driver disassembles quite a bit easier. The symbols seem to match up and give IDA better hints at what's going on. And mostly it was classic bottom-up analysis. I'm looking for mem-move, mem-copy, all of the dozen or so EX-allocate pool routines that are there. All of those look good. So there's probably 200 cross-references to these routines. You go look at one. You say, is there a way to make the buffer overflow with a long length, or is the buffer appropriately sized? Is it aligned properly? These are fairly well-documented techniques for finding bugs in kernel drivers, and it's just a manual slog through it. The other technique I like to use on drivers is to cross-reference security check cookie. So the compiler is kind enough to tell you that, oh, there's lots of stack operations here, there's lots of copying, there's a large stack buffer. I'm going to put a cookie there, and I'm going to check it on the way out. Well, if I go through all of those functions, I'm guaranteed to find good opportunities for vulnerability analysis. Likewise, functions with large stack buffers that may not have a cookie on them for one reason or another were also a target for analysis. And then the one that I really love to have a solid automated story for, but I don't, is object reference counting bugs in this. There are several instances where references are increased, and every code path that I did data flow analysis on and control flow analysis on showed that these were being used appropriately. So Microsoft did a really good job writing this driver. You could tell that it had been looked at manually. You could tell that it had been fuzzed going through it. And this is kind of indicative of the bugs that they were getting out of it too. So the bug last year was a dangling pointer reference. So this was an object reference issue. So there's a couple of scripts I wrote that would automate checking for returns, like when you call EX-allocate pool, can you verify that you got a pointer back? And there was one that really kind of it caught me for a little bit, was tag priority, which actually doesn't return a bad value when it has a problem. It raises an exception, which is different from all of the other EX-allocate pool routines. So I went through all of the reachable ioctls. I did not go through WSK, and I did not go through SAN because you do have to have a SAN device enabled to reach a lot of them. They paid very good attention to data alignment and proper size restrictions on any buffers you passed in. And the majority of the ioctls were passed as method neither. So method neither, you get basically the I/O manager doesn't copy any of your data. You get pointers directly to user mode. And this is sort of the reason why you have a lot of bugs in Win32k sys, is because many of those ioctls are also method neither, and you can get into time of check, time of use bugs very quickly. So I manually checked for these as well, along with integer issues. The fuzzing bit, I banged my head against this for 3 or 4 weeks, and I had a frustrating time with it because I wasn't finding bugs. So when you get frustrated, I'm just going to throw all the crap at the thing and see what happens. So I wrote up a quick fuzzer, and I had a pretty good understanding of what it was actually doing with ioctls, what the limits were, that you couldn't pass in more than 256 bytes for a AFD bind request. So I built these this knowledge into the fuzzer when I went to fuzz the object. So it wasn't wasting a whole lot of time fuzzing things that were kicked out, at first glance at the function. And this is my preference. I usually like to do static analysis over fuzzing because you get a better understanding. And if you're going to go the route of fuzzing, I would encourage you to do static analysis first, because I think you're going to write a better fuzzer in the end, having some knowledge of what it's doing. So I had 2 weeks of fuzz time off it. I did not scale it. I had a single core running. I basically had 2 VMs, one running my fuzzer, one doing a kernel debugger back to it, so if an exception happened, I would catch it and be able to analyze real time. I had it was kind of a simple fuzzer with maybe one little novel technique. It would hit all of the ioctls, and it would then have the buffers that were passed into these ioctls mutated by a separate user mode thread, so that we could attempt to find these time of check, time of use bugs. Now there's a race condition there that you're not likely to win unless you line things on page boundaries, but if you're going to scale this, I think that you're likely to hit it at least once or twice. So the fuzzer did not turn up anything, which was not terribly surprising given the quality of the code, but we did have at least a poke at it. So for a little bit of future work, it's really interesting to say that you can have this sandbox and you can't make socket calls, but it is technically possible to write a native AFD library. And I say native, like you could link in AFD_socket, and even though you don't have the whole WinSock framework supporting you, so long as you can talk to this driver in the right way, you'll be able to get socket communications out of a sandbox with it. And you could compile this right into shellcode. And the really cool thing about doing something like this is that it would apply feedback into a more intelligent fuzzer. So instead of fuzzing with these ioctl calls, you then fuzz off of the library. And that's something that's about half implemented before we stopped research on this. So the intent was to provide some level of assurance that AFD is not going to fall over with 3 or 4 weeks of analysis. I think we could fuzz better. We could fuzz at scale, and we could build out the data structures that it's expecting a little bit more. And if it's useful, I don't know how many devices are out that have SAN access in them. We could fuzz the SAN functions as well. So that's my talk. It is a 30-minute talk, so kind of a short, brief intro into WinSock and AFD. Big thanks to Google and Project Zero and James Forshaw for supporting this research and encouraging me along the way. Happy to take any questions that you have about Project Zero, AFD, anything along those lines. No heckling? Yes. Oh, well. Mike?
I just wanted to ask a personal curiosity. Have you tried to do this kind of research even with an NDIS or a Windows Soccer kernel driver?
No, so we were not so much interested in that under the sandbox sort of focus.
Okay. Thank you.
There's one behind you.
Hi, I have, I guess, a general question that goes with what you were doing. Do you guys document your fuzzers at all, or kind of provide any frameworks or baselines for what you guys are doing there?
Yeah, so we've certainly released fuzzers to Microsoft in the past. We've released, well, not Project Zero specifically, but the team members on Project Zero have released open source fuzzers. Our experience is that they've largely sat on the shelf, so it's not something we strive to do. If it is requested, certainly we can release it. I think for this one in particular, if we're going to go back to it, I'd focus on the native AFD library first, and then build a fuzzer around that, and possibly release both. Okay, thank you very much.